আমরা এই অকুপেশন নাম্বার, হ্যাঁ, এই যে জিআই যেগুলো বলেছিলাম সেগুলো কাইন্ড অফ গ্রুপিং দ্য এনার্জি লেভেলস। হ্যাঁ, এনার্জি লেভেলস তোমার সিস্টেমে এনার্জি লেভেলস আছে, সেগুলোকে গ্রুপ করেছিলাম আর কি। হ্যাঁ, সেগুলো আমরা ডিজেনারেশন নাম দিয়েছিলাম, বাট দে ওয়ার গ্রুপড। হুম। হ্যালো, আচ্ছা আমি কতক্ষণ আগে কেটে গেছিলাম?
স্যার আমি তো মানে কিছুই শুনতে পাইনি, আপনি জাস্ট স্টার্ট করলেন তারপর থেকে আর শুনতে পাইনি।
ও, আমি কিছু একটা জিজ্ঞাসা করতে গেলাম, গিয়েই দেখছি যে কোনো উত্তর নেই, তারপর দেখি যে আমার মানে ইমিডিয়েটলি নেট চলে গেছে। আচ্ছা আমি দাঁড়াও আবার যাই। আচ্ছা দেখো তো, এইগুলো দেখেছো? এইগুলো আমি বললাম, এইগুলো দেখেছো?
হ্যাঁ, yes, sir.
আচ্ছা, এইখানটা
উম,
হ্যালো, হ্যালো।
মানে
হ্যালো।
দেখেছি কিনা সেটাই বলছেন আপনি? এটা
আচ্ছা বলছি যে মানে সাউন্ড কি ক্লিয়ার আসছে না?
ক্লিয়ার স্যার।
ওকে। আচ্ছা এই জায়গাটা দেখেছো? আমি যখন বলছিলাম তখন কি নেট ছিল?
না,
আচ্ছা এই জায়গাটা, এই রেড পোর্শনটা।
লেট পোর্শনটার টাইমে আমার কাছে তো ছিল না।
না
আমি
স্যার, ছিল না।
ভাবছি-
আচ্ছা ওকে 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 ওকে, এই জায়গাটা, এই জি এর এক্সপ্রেশন গুলো।
না স্যার, মানে আপনি পড়াতে স্টার্ট করেছেন তখনই মানে হয়ে গেছে।
ও আচ্ছা আচ্ছা আচ্ছা, ঠিক আছে। ওকে, so basically what I'm saying is that we start with the canonical partition function. আচ্ছা, তোমরা একটা কাজ করবে, তো যদি আমি তো ধরো পড়াচ্ছি, আমি তো বুঝতে পারছি না নেট আছে কিনা, দেন ইউ গিভ মি আ হোয়াটসঅ্যাপ নোট, হ্যাঁ, যদি চলে যায় মাঝখানে। হুম।
ওকে স্যার।
হ্যাঁ, তো এটা হচ্ছে canonical partition function. We are writing like this. We know this definition, and beta is 1 by kbt. কেউ কি এলো? Beta is 1 by kbt. Now E of course has to be n epsilon E epsilon, where n epsilon number of particles are in the state epsilon. Okay, so in the beginning what I said, that we have the energy levels for the system, then we are grouping the levels. Okay, some bunch of levels we are assigning to a single level with the degeneracy Gi. That is what we did, even though I did not mention it earlier, but we did that. Okay, and look at path 3 also. Okay, now now the point is that n epsilon has to be, if you sum over all epsilon, then a total number of particles has to be reflected. Now in general you write it in terms of, as we had a grouping of energy levels, and then you have to have the partition function, canonical partition function, in this way, where this represents the set of the set of distribution. Okay, now um, uh, now what we are going to do here, statistical weight factor is written like this in case of different statistics, and the particles obeying different statistics. Now for Bose-Einstein statistics, hello, শুনতে পাচ্ছো? Hello.
হ্যাঁ
Yes,
স্যার।
sir.
হ্যাঁ স্যার, পাচ্ছেন।
না মাঝে মাঝে ঘুরপাক খাচ্ছে, আমি একটু মানে ভিজল লিটল বিট। ওকে, so both instant condensation, this has to be in this case actually what we are doing, we are in the present case, the treatment is that we are dealing with the single particle states as individual states, no more grouping. Okay, without requiring them to be grouped into sets. Thus, G and epsilon may be obtained directly by putting Gi equals to 1 in our weight factors, the W. Okay, so and here you see this one, G, both G, the single particle occupation definitely has to be 1, but Fermi-Dirac particle, it has to be 1 if there is no particle or there is a one particle, or otherwise it will be 0. Obviously, and Maxwell-Boltzmann, it should be like this, because if you look at the W, then n, if you make Gi equals to 1, now there is no grouping, then it is 1, product of 1 is 1. Fermi-Dirac, you will see that it will be reasonable when 1 0 or 1 equals to I, Gi equals to Ni equals to sorry Gi equals to 1, if you put, then it will be reasonable for if your Ni is 0 or 1, otherwise physical. And for Maxwell-Boltzmann, Gi equals to 1 by n epsilon Ni factorial over I, and I is replaced by epsilon, and that is why it is written Maxwell-Boltzmann is 1 by n epsilon factorial. This is 1 if there is a 0 particle or 1 particle. It cannot have more than 1 particle, and for otherwise 0, and both probability weight factor is 1. With using these weight factors, what we are going to do, we are going to look at the partition function, canonical partition function first, for the Maxwell-Boltzmann case. That means we use the G like this, and then we put the G value here, and then next step is that we are writing n factorial deliberately here, dividing and multiplying there. Then, because if you expand it, then of course sum over all possible sets of n epsilon, then it will look like this. And if you sum over all possible set of n epsilons, then it will be multinomial distribution kind, and therefore you can write it as 1 by n factorial whole to the power n, and therefore you can write it this one. You can write it as sum over epsilon eta minus beta epsilon to the power n, and that has been written here. Qn by Vt, that is the canonical partition function, is 1 by n factorial. This Qn is this, and of course then you identify this as the single particle partition function. Now this is identical with the result we obtained earlier, right? If you recall, then you see that is the result we obtained earlier. Now evaluation of Q1 beta, of course, I mean straightforward, we obtain using the asymptotic formula density of states. Okay, so sum over sum goes to because V is very large, energies are more or less continuous, and therefore you can use the density of states in this case. You have already calculated the density or expression for the density of states. It goes as e to the power half, and therefore for single particle you have introduced the density of states here, and that's how you have gone over from some summation to integration. We have taken over, and eventually it will be in this form. Okay, this is the form, this is the form, and this lambda is identified as the thermal wavelength. Okay, this is the known expression lambda, which is called thermal wavelength, h by square root of 2I pi mkt. Remember this. Okay, this is thermal wavelength, so this is v by n, v by lambda cube. This is what you have here. You see, now for n particles, certainly n particle partition function has to be q1 to the power n by n factorial, and therefore this is the expression. Now then there is a relation. You have already obtained the relation between grand partition function and the canonical partition function, which is in terms of fugacity. And you see, this is the grand partition function. This is a to the power n q1 vt, and sum over n equals 0 to infinity. And this is, just you put the expression. Eventually, you get this exponential of ZV by lambda q. The thermodynamics of the system follows equally well from the grand partition function. Of course, I mean, there is a partition function, then certainly there are certain relations, thermodynamic, some relations which connect to the thermodynamics, and hence you can obtain all possible quantities. Now consider the Bose case and the Fermi-Dirac case. Now Q and Vt is this, as we said, this for Bose, this is 1, and for Fermi-Dirac is 1 and 0, and therefore so B, the Q and Vt equals to this, and the difference between the quantum cases, namely Fermi-Dirac and Bose, arises from the value of the numbers n epsilon can take, right? Now you see, here, in view of the restriction of the condition that n epsilon sum over n equals to n on the summation, this summation cannot be anything. It has to be those for which this is satisfied. An explicit evaluation of the canonical partition function is rather cumbersome. On the other hand, the grand partition function turns out to be more easily tractable. Let's see. This q is j to the power n, and this is your expression, and then certainly you can have this sum here, and then this sum is there, and you can write it as this product form. Certainly this is another way of writing it. The double summation first over the number epsilon and epsilon under the constant of total number, that is total number sum over n epsilon has to be n, and is equal to the summation over all possible values of numbers in epsilon independently of one another. Hence, we can write, you see, this is the set, right? Now this is sum over the number n equals to 0 to infinity, and this is the set. If you combine these two, then you can have the summation over all the numbers n0, n1, n2, and so on, and then n0, n1 is running from 0, 1, 2, all possible numbers. Okay, so you just think over it a little bit, and then you will find that these two are consistent. Okay, if you can write this in this form, because this set contains n0, n1, n2, and so on, and you will, if you combine them, then you will find that you can take a simple example and then work it out, and you will find you can write it in this form where n0 is running from 1, 2, 3, 4, and so on. Okay, so this is the expression you can have, and then this can be written as like this: 1 by 1 by z minus 1 by 1 minus z e to the power minus beta epsilon. Of course, assuming the convergence, and then this is the product, because every term will give you this type of thing: 1 by 1 minus z e to the power minus beta epsilon 0, then 1 by 1 minus z e to the power minus beta epsilon 1, and so on. You write it in the product form with the notation index the epsilon, and therefore QBE Rosenstein is like this. For Fermi-Dirac expression, why we are doing all these things these will be required when we talk about the Bose gas condensation and Fermi gas properties. Okay, then we'll require these expressions. Now, Fermi-Dirac case and epsilon case. Acha, you have already done this, right? তোমরা তো project submit করে দিয়েছো না? Hello?
না স্যার, মানে এখনো প্রজেক্ট সাবমিট করা হয়নি, আজকে করবো।
তো অনেকেই তো করে দিয়েছো। তো মোটামুটি তোমরা এগুলো সম্বন্ধে পরিচিত, তো তোমরা তো নিশ্চয়ই প্যাট্রিয়াকে ডেফিনেটলি ফলো করেছো।
এই
হ্যাঁ স্যার,
আগেরটা এই পার্টটা পড়ি।
করনি সমস্যা?
স্যার পাত্রিয়া তো ফলো করেছি, কিন্তু ওই ক্যানোনিক্যাল এনসেম্বল, গ্র্যান্ড ক্যানোনিক্যাল, মাইক্রো ক্যানোনিক্যাল ওই সবগুলো করেছি। তারপর ওই এক্সাম্পল গুলো আপনি যেগুলো পড়িয়েছিলেন, লিনিয়ার হারমোনিক অসিলেটর, তারপর ফ্রি পার্টিকেল ইন আ বক্স, ওইটাই করেছি। এই দিকটা তো ফলো করিনি, মানে যতটুকু ডেনসিটি ম্যাট্রিক্স এর কনসেপ্ট আছে আর মানে এখানে তো আসেনি একদম।
সময় Okay, so in Fermi-Dirac case, as I said, you see that this is n epsilon could be 0 or 1, and therefore you can have the sum. For both case, you had sum of with all possible values, but here with a 0 or 1, and therefore 0 and 1, two possible things, and therefore if you put 0, then this is 1. If you put n0 equals to 0, then it should be.
বলছি আমি মিডলে কিছু শুনতে পাইনি, মানে যখন আপনি কোশ্চেন করলেন তারপরে মানে আমি আর সমস্যা যে বললাম তারপরে কিছু শুনতে পাইনি। আপনি কিছু
না, তারপর কিছু বলিনি আমি। হ্যাঁ, তারপরে কিছু বলিনি। আমার একটা মিটিং ছিল, সেটা আমি লিখে দিলাম যে ডিপার্টমেন্টাল মিটিং, যে ডিপার্টমেন্টাল মিটিং আমি থাকতে পারবো না।
আচ্ছা,
সো Okay, all right. So basically, you see n epsilon now. Yeah, just after that, I started with the Fermi-Dirac case where this one as usual relation here, but in this case, n epsilon runs from 0 to 1. Okay, not all possible values, as in case of Bose case, Bose statistical case. So in this case, n0 can have 0 or 1, and here all it could be all levels could have 0 particle or 1 particle, and therefore the sum is running from 0 to 1. So if you 0, this is 1, and if it is 1, then this will give you this, and therefore all these terms will have similar this like this term, and therefore you have the product of epsilon, and eventually q. This is the grand partition function for Fermi-Dirac case, particle obeying the Fermi-Dirac statistics. The grand partition function is. You know that grand potential, that Q, that potential that you could write in terms of PV by KT, and you know PV by KT is ln of this Q that we already defined earlier, right? When we were talking about the grand partition function, and we already introduced a potential, Q potential. There's the grand potential, and that is PV by KT is like this, and this Q can be, you can write. The expression is different for different statistics. So this minus goes for the Bose statistics, and this plus goes for the Fermi statistics. So this is the relation between Q potential, and once you know the Q potential, you know many quantities, right? In general form, if you want to write this in a general form, all these three statistics, if you can write in a package, then it would be Q equals to 1 by A sum over epsilon ln 1 plus z e to the minus beta epsilon. You see, when A equals to 0, then it will lead to the case for Maxwell-Boltzmann statistics, and if it is plus 1, then it will lead to the Fermi-Dirac one, and if it's minus 1, it will lead to the at least you can see if it is minus 1, this is minus, and this is minus, so it goes to the Bose. If it is plus, this is plus, and this is plus, it goes to the Fermi. But how is the Maxwell's Boltzmann distribution? If A tends to 0, then you see apparently it will look like as if apparently it would look like as if it is infinite, but it's not, because ln of 1 plus z, ln of 1 plus x on x tending to 0 is x, and therefore as A tends to 0, then ln of 1 plus az it will give you az e to the minus beta epsilon. A will cancel, it will give you z e to the minus beta epsilon. Some of them. This is what it is. If A tends to 0, this would be equal to. So ln of this, it will reflect this one, and A will cancel and look at 6. This is Z. Okay, now recall n. In statistical mechanics, this is one problem that you have to remember certain formulas. This total number of particles n is Z del Q del Z Vt. So you have to recall this grand partition function. And if you do this in general, this is the package. Okay, this is for all statistics, Bose statistics, Fermi-Dirac statistics, or the classical statistics, where a 0 or plus 1, 0 corresponds to Bose classical Maxwell-Boltzmann, a plus 1 is Fermi-Dirac, and a minus 1 is the Bose. Now you can do this, and now again you have to do all these things. You have to do by yourself these derivatives, and eventually you will find that it turns out to be like this. Okay, so n equals to this, and what is u? U is, again, you have to borrow the formula, you have to recall the formula, and eventually if you do this is u. And this is for all statistics with A. Now, in average, again, you use the formulas, just you have to do by yourself. Derivatives. All I can point out that here you see you are doing the derivative with respect to 1 epsilon, and all other epsilons are constant. Okay, that you have to take into account. Otherwise, you'll be confused from this. Okay, so then it will give you like this. What is this? This gives you average occupation number. So this is nothing but the average occupation number, right? This is the average occupation number. And you know that many times you have seen that average occupation and most probable occupation is the same, and this is what it is. And now if you plot all these things, then Bose-Einstein statistics, it will be like this. Fermi-Dirac will be 1 below, if you look at this, if you analyze, this is your expression. And now A equals 2 plus 1 is the Fermi-Dirac, minus 1 is the Bose, and 0 is the Maxwell-Boltzmann distribution. Now, if you plot all these things, if you analyze this, now you see for Fermi-Dirac, we have already seen it goes like this. Occupation, it is 1, and then it deviates at finite temperature. And so this is epsilon equals to mu. This is the kind of, as we say, is kind of Fermi energy type. And then the Maxwell-Boltzmann distribution is like this, and Bose-Einstein diverges at this, and on physical this side. Okay. So this, if you look at this expression, you see in case of Bose-Einstein distribution, it is like this, right? Now see for epsilon less than mu. If epsilon is less than mu, then n epsilon is negative, right? If epsilon is less than mu, then it is negative, which is unphysical. Therefore, in case of Bose-Einstein statistics, you must have mu less than epsilon, and this should hold good for all epsilons. Otherwise, some of the mean occupation numbers will be negative, right? And look, when mu becomes equal to the lowest value of epsilon, say epsilon 0, the occupation number corresponding to that level tends to infinity. This in turn leads to Bose-Einstein condensation. That has been shown here. That it goes to infinity. Okay. Now, however, for again, you see for mu less than epsilon naught, mu less than epsilon, the value epsilon minus mu are all positive, and behavior of all this average quantity is non-singular. Finally, in the Maxwell-Boltzmann distribution case, A equals to 0, a mean occupation number takes the form like this. Okay, you can write it in this form, and if you sum over all this epsilon, then it will be like this. This is equals to the total number, and therefore n epsilon average equals to n into this. Therefore, n average by n is the probability of occupation of the state of the particle is given by this. All these are deflected, right? Now, physical interpretation of the classical limit, you see. Now, n epsilon, this is occupation number. From this, we note that the distinction between quantum statistics and classical statistics become important when the role of the parameter A becomes unimportant. When A is unimportant, then it goes to classical statistics because it is e to the power minus mu epsilon minus mu by kBt. That is the Maxwell-Boltzmann distribution, right? So this happens if all the values of epsilons that are of practical interest, then epsilon, this has to be this quantity has to be very greater than 1, right? And that means n epsilon is very less than 1. Okay. Now we know that sum over epsilon and epsilon is like this equals to 1, and therefore, that we have already seen z given by the equals to n. Okay. So these are the kind of analysis that you have the expression. You have the expression for occupation probability, and Fermi-Dirac occupation probability that we have. We all know about it, right? All of you already aware of these kind of distributions, and only thing that you are trying to analyze this and compare all these three graphically. Okay, so basically, as t goes to t becomes there are few things. Fermi-Dirac distribution is like this, Maxwell-Boltzmann distribution is like this, and Bose-Einstein diverges. It actually indicates kind of condensation. Okay. Now, having said these things, This is kind of again repetition that Z Q1 beta equals to N. For large values of this, the quantum curves 1, 2 approaches the classical curve 3 that we have already shown those curves. So basically, if this is pretty large, then whatever A is plus 1, minus 1 or 0, they'll be neglected, right? So all will go over to the classical. That is what it means. Since we already know that the higher temperature of the system, the better the validity of classical treatment. Therefore, the condition, you see, this is important actually. You know that you have seen in many cases that as temperature is very large at higher temperature, then system reflects the classical result, right? Then at higher temperature, and again all the statistics will approach the classical one if this one is pretty large. This implies, so again you read, since we already know that the higher temperature of the system, at the higher temperature, the higher the temperature of the system, the better the validity of classical treatment. Therefore, the condition this greater than 1 implies that the chemical potential mu must be negative and large in magnitude, because otherwise there is a conflict, right? Because unless and otherwise this mu is negative and large, then you cannot have this one. It's very, very greater than 1, because T is very large, right? At T large, you have the classical result. That means it goes over to the classical statistics. Then the entire statistics would go to the classical one. Therefore, this quantity has to be pretty large. And then there is only option is that mu has to be pretty large and negative. Otherwise, it cannot be. So this means that the fugacity Z exponential mu by kVt of the system must be much smaller than unity. Okay, that is Z is very, very less than 1. Now, because if mu is negative and large, then it has to be 1. It can maximum, actually the upper bound of chemical potential is 0. Okay, it can run up to 1 for at least for the. Now Z equals to, then what we can see that we already said that Z equals to Q1 beta from here, and also earlier also we said, as I remember somewhere. Did I say that somewhere? No. Oh, I did not say this earlier. Okay, then you can have this once again. You can look at this. You have separated this, and this is one beta, and this sum over average n over all epsilon, of course, has to be total number, and therefore this is the relation. And this relation is taken here. This n by q1 is less than 1. We know for ideal gas q1 beta, ideal gas, okay, for q1 beta is v by lambda q. That we have already seen, right? And therefore lambda, and where lambda is equal to the thermal wavelength, this h by this. Okay, then you see that Z is less than 1. That means n by q1. N by q1 is this. This is pretty less than 1. Okay, and then n lambda q by v is pretty less than 1. And this n by capital V is the number density, right? So small n, you can write it as small n. Lambda q is less than 1. That is what we have written. N lambda q is less than. So this is the classical limit. All we did here in this part is to see that n lambda q is our determining parameter. Okay, lambda is the thermal wavelength. So, okay, so n lambda q, n is the number density. N lambda q is very, very less than 1. That is the classical limit. Okay. Sorry. Okay, so this is the classical limit. Now fluctuation. Now we have seen earlier that again you bring or recall the quantities here. I mean the relations here. Then again you see n average is this, and this is quite, you are quite familiar with this, right? This occupation number. Then n square average you calculate, and then from this you get the fluctuation. You go through this, okay? I have explicitly written it here. Just you go through this and see the kind of fluctuations you have. You'll have the fluctuations of this one. This A is in general, okay? Because use this. A0 is this, A1 is this, and for A minus 1 is this, the fluctuations. These are called below normal, above normal because +1, and this is the normal fluctuation in classical case. This is 1 minus below normal, and this is called above normal. So these are the terminologies, but you look at the fluctuations, how it goes. Now, for better understanding the statistics occupation number, let us evaluate the P epsilon n. What is P epsilon n? Is the probability that there are exactly n particles in the state of epsilon, energy epsilon. That you see, for fermions, n epsilon is sum over n equals to 0 to 1 n P epsilon n, right? Because in each one it can have 0 or 1 particle, and therefore you get 0 into this plus 1 into this is a P1. These are simple relations, P epsilon 1 is this, and then P epsilon 0 should be 1 minus this. And for most case, you have this. Now you have no restriction on this number, and you have, you can evaluate the probability like this. And eventually you'll have the expression for probability. It's like this, okay? For both Einstein case. Simple algebraic calculations, you can just carry on. And then Maxwell's case, eventually, if you do the same thing, then eventually we'll find the probability it turns out to be. Are you familiar with this kind of distribution, probability distribution? Look at this distribution. So I'm not doing explicitly this calculation. I have done it here. Just you go through, okay? You go through this, and eventually we'll get this, expression. Because your n average, in case of classical case, n average is z e to the power minus beta epsilon. This is the n average, right? So you write this at the n average to n. Are you familiar with this kind of distribution? Have you seen somewhere, anywhere?
হ্যাঁ স্যার
কোথায় দেখেছো?
স্যার কোহারেন্ট স্টেট যখন পড়েছিলাম তখন দেখেছিলাম যে ওই স্টেটগুলো এই ধরনের ডিস্ট্রিবিউশন মেনে চলে।
কি ডিস্ট্রিবিউশন বলে এটা?
পয়সন ডিস্ট্রিবিউশন।
আচ্ছা, কে বলে? নন্দিনী বললে? অভিনন্দা কে বললে? নন্দিনী, আমি কি তোমাদের না আমি তোমাদের বিএসসি তে ম্যাথ পড়াইনি না?
হ্যাঁ স্যার, বিএসসি তে কমপ্লেক্স অ্যানালিসিস পড়িয়েছিলেন।
বিএসসি থার্ড পড়িয়েছিলাম না? বিএসসি থার্ড ইয়ারে
কমপ্লেক্স অ্যানালিসিসটা পড়ে,
কমপ্লেক্স অ্যানালিসিস পড়েছিলাম। প্রবাবিলিটি ছিল না? প্রবাবিলিটি ছিল না বোধহয় না?
হ্যাঁ প্রবাবিলিটি ছিল, প্রবাবিলিটি ছিল।
তাহলে তো এটা অবশ্যই ছিল।
হ্যাঁ ছিল।
তাহলে সেই কেবেলের অঙ্ক মনে আছে? কেবেলের অঙ্ক, কেবেলের নাম্বার অফ ফ্লজ।
হ্যাঁ স্যার, হ্যাঁ।
তাহলে কোহেরেন্স সেটটা মনে আছে, কিন্তু আমি তোমাদের পড়িয়েছিলাম সেটা মনে নাই কেন? Discredit anyway. So these are the things you have to wrap up, okay? At your home, you have to sit down with pen and paper, and you have to go through these things, okay? Just overall I gave I went through overall. Nothing much is there. Basically most of the formulas that you have already learned, you have to borrow, and you have to go step by step, and you have to calculate this grand partition function, then average number of particles, then energy, and then for different distribution you will have different things, and you have to see when all these distribution merges at which condition. Those are the conditions, and eventually it reflected that mu has to be positive, large number but negative in value, and so on. And also this distribution itself tells you that since the mathematically it diverges here, and therefore it will probably correspond to Bose-Einstein condensation. Now, with this, let me go to distribution mechanics. Let me look at this. Now let me go to actual ideal Bose gas system. You have heard a lot about Bose-Einstein condensation and so on, right? So now let us look at the properties of Bose or the gas, non-interacting gas obeying the Bose statistics. Okay. Now that's what we are saying, that we shall investigate the detailed physical behavior of a class of systems in which, while the interactions are negligible, the effect of quantum statistics are important. Okay. So basically, these are quantum statistics, right? If the particles are bosons, they will be the Bose statistics means they are obeying quantum statistics. This means that temperature T, that the temperature T and the particle density of the system do not conform to the criteria. This, okay. I'm exactly ditto following path here, okay. Only thing what I have done at some places, the calculations are not given somewhere. So I have just, filled the blanks. Now, this is n lambda q by v, n lambda q. This is less than 1. This is, what is this condition? This condition for, just answer me, what is this condition? N lambda q is equal to less than 1.
মানে ইকুয়েশনটা ক্লাসিক্যাল আছে না কোয়ান্টাম মেকানিক্যালি ট্রিট করতে হবে
at this limit,
ক্লাসিক্যালি ট্রিট করা যাবে।
at this limit it goes to classical, right?
হ্যাঁ স্যার।
Yeah. So basically, that is why it is saying that this means that and the temperature T and particle density of the system do not conform to the criteria. This, okay. And এটা হলে আমরা classically চলে যাব. Now, when n lambda q tends to 0, all physical properties goes over to the classical counterparts. As I said, it was pretty less than 1, then it goes to the classical counterpart. Again, T tending to infinity, and lambda tending to 0. If T tending to infinity means lambda tending to 0, right? Then n lambda tending to n lambda q tends to 0, right? That is also classical, because we know at large temperature, then lambda tends to 0. Then n lambda q will definitely go to 0, right? Will tend to 0, and therefore it's a classical. In this way also you can understand. Okay, it will go to the classicalism. Now, for small but not negligible small, yet small value of n lambda q, various quantities pertaining to the system can be expanded in power series in this parameter. So this is an important parameter, n lambda q. From these expansions, one obtains the first glimpse of the analytical manner in which a departure from the classical behavior sets in. Okay. So if you can expand in terms of this, then probably you can have an idea about how it is analytically switching over to the classical behavior. When n lambda q becomes of the order of unity, then not only does the behavior of physical system exhibit a significant departure from the typical classical behavior, but it also influences by the fact whether the particles obey both Einstein statistics or Fermi-Dirac statistics. That means when n lambda q tends to 1, it approaches of the order of unity, then there is a kind of departure, and there it again depends on whether that obeys both Einstein statistics or Fermi-Dirac statistics. Here we consider the system obeying the Bose-Einstein statistics. Now, in general, again we recall that Q potential, that is PV by KT, is ln grand partition function equals to this in general, right? Now n equals to this, and for Bose gas we will put n a equals to -1, right? And therefore PV by KT, you see this is the relation, PV by KT equals to this, and n equals to sum over all average numbers occupying the states, sum over states, and that is this. And beta and Z is the fugacity, you know already. Now, since we are dealing with a system which is very large in volume, the summation, the spectrum of the single particle state epsilon p of the system is almost a continuous one. I have given the logic many times that the system is pretty large. Then this summation, probably summation over epsilon, this state will go over to the single particle state dispersion relations, and it will be continuous one. Okay, and therefore now, since these are non-interacting particles, free particles, then we will borrow the dispersion relation and the dispersion or dispersion relation of the free particles, and hence the density of states corresponding to free particles, those are non-interacting particles, are this. This we have used many times, we have derived earlier many times. So this is the expression for the density of states. Now look, by straightforward replacement of the summation by integration. Now this summation has to be replaced by integration using this density of states. Now we are going once we just by straightforward we just replace the summation by integration, then we are going to miss something. What is that? We are giving zero weightage, because this is epsilon to the power half, right? For 0, we are giving a zero weightage to the epsilon equals to 0 state. This is wrong, because in quantum mechanics treatment we have to give weightage 1 to all the states. এই জায়গাটা বোঝার চেষ্টা করো। এই জায়গাটা আমি যেটা বলতে চাইছি, আমি ইন্টিগ্রেশনটা কোথায়, এই যে ইন্টিগ্রেশন, আমি এই যে সামেশনটা, এই সামেশনটাকে আমি ইন্টিগ্রেশন দিয়ে রিপ্লেস করব এই ডেনসিটি অফ স্টেটসকে ইউজ করে। কিন্তু সেখানে আমি যদি ডিরেক্ট জাস্ট এইভাবে বসিয়ে দিই, তাহলে কিন্তু এপসাইলন ইকুয়ালস টু 0 কেসটা 0 হয়ে যাবে, রাইট? কারণ তুমি যদি মানে ইন্টিগ্রেশন ইজ নাথিং বাট সাম, রাইট, ইন এ কন্টিনিউয়াস ফ্যাশন। বাট ফর এপসাইলন ইকুয়ালস টু 0 যে স্টেটটা থাকবে, সেই স্টেটটার ওয়েটেজ 0 হয়ে যাবে, কারণ এটা 0 হয়ে যাবে। হ্যাঁ, therefore that 0 state is not taken into account, right? But quantum mechanically you have to give, as for both case, you have to give according to quantum treatment, we have to give weightage 1 to all states, and therefore you see in that summation what we have done, we have taken that 0 state, epsilon equals to 0 state, well, epsilon equals to 0 state, we have taken out from this sum, and then the rest of the sum has been done with the intensity of states. That is what we have done, you see. And you just ask me a question if you have a doubt in this portion. This is important. PV/KT is, you have the sum, you had the sum, and then I have taken the first term out, because in this case, in the first term, if epsilon equals to 0, then it will be ln of 1 minus z, right? Ln of 1 minus z, you see. I have written minus ln of 1 minus z. Then the next term is minus, then integration over epsilon d epsilon and this, okay, and you see, then minus a epsilon d epsilon and this ln this. But here you see, even though I have included 0, limit 0 in the lower limit 0, but 0 limit at 0, this epsilon will be 0, and therefore it will not contribute the 0 term, right? 0th term, and therefore including 0th term or not including is the same thing, and therefore for convenience we have taken the limit from 0 to infinity. Okay, so this is what we have done here. In this expression has rewritten for a continuous energy levels, we have written in this form. So do you have any problem, I mean any problem in understanding this? Mojumi?
স্যার বলছি, মানে এখানে যেটা যে মানে বললেন কি এপসাইলন 0টা 0 হয়ে গেছে, ওয়েটেজ ফ্যাক্টরটা, ওটা কেন হলো ঠিক বুঝতে পারলাম না।
কোনটা বলো তো, কোন জায়গাটা?
মানে একটু আগে যেখানে যে বুঝাচ্ছিলেন, একটু স্ক্রল করুন, উপরে যান। হ্যাঁ, এখানে।
আচ্ছা, এইখানে আমি যেটা বলছি, আমি এই যে সামটা আছে, হ্যাঁ, it includes all the energy levels 0, 1, 2, 3 and whatever energies we have, right? Now this energy spacing is pretty small, okay, because system is pretty large, V is large, and therefore you can replace the sum by integration, right? Now you see, you can write this as the 0th term, sum over first 0th term and then non-zeroth term. Okay, you can write this sum as, for example, so probably no, you can write it as this one. You can write it as minus, say, the term epsilon equals to 0 term, say minus 1 minus z. Okay, because epsilon 0 means e to the power 0 is 1. If you put epsilon equals to 0, this is the epsilon equals 0 term. Okay, this ln, sorry, ln. Okay, now minus sum over, say, epsilon not equals to 0, not equals to 0. লেখাটা ঠিক হচ্ছে না, but you can probably understand. ln of 1 minus z e to the power minus beta epsilon. তাই তো, এটা মানছো তো?
হ্যাঁ স্যার।
আচ্ছা, এইবার এই যে টার্মটা, এই টার্মটা হচ্ছে epsilon equals 0, এই টার্মটা হচ্ছে epsilon not equals to 0, ঠিক আছে? এবার এখানে আমি যেটা করছি, এইখানে আমি এই ডেনসিটি অফ স্টেটস এর ব্যাপারটা নিয়ে আসছি। এই যে এ epsilon সামেশনটাকে আমি যদি ইয়ে করে দিই, তুলে দিই, তাহলে এখানে কি হবে, ইন্টিগ্রেশন এ epsilon d epsilon, রাইট? আর এটা থাকবে। এখন এই যে এ epsilon d epsilon, তাহলে আমি এখানে তো আবার যদি লিমিটটা 0 to infinity করে দিই, তাহলে 0 টার্মটা ইনক্লুড করে নিচ্ছি, তাই তো? কিন্তু 0 টার্মটা ইনক্লুড করলেও যেহেতু epsilon 0 তে এটা 0, হ্যাঁ, সেই জন্য 0 টার্মটা ইনক্লুড করা না করা ইন্টিগ্রেশনের মধ্যে, এই ইন্টিগ্রেশনের মধ্যে আর কি, ইন্টিগ্রেশনের মধ্যে 0 টার্মটা ইনক্লুড করা না করা একই ব্যাপার। মানে ইট ইজ অ্যাজ ইফ epsilon not equals to 0, সাম ওভার epsilon not equals to 0, এটাই আমি বললাম।
আচ্ছা,
বুঝতে পারলে?
মানে সবটাই ক্ষেত্রে ওয়েট ফ্যাক্টরটাকে 1 করে দেওয়া হবে, ওটা কি বললেন? ওটা আরেকবার বলুন তো লাইনটা।
হ্যাঁ, ওইটা বললাম যে তোমার ওয়েট ফ্যাক্টরটা সেই জি is 1, right? For any state that weight factor is 1.
ও
Okay?
আচ্ছা, হ্যাঁ।
হ্যাঁ, সুতরাং তুমি জিরোটাকে জিরো করতে পারবে না আর কি। তুমি যদি আলাদা করে epsilon 0 টার্মটা যদি আলাদা করে না নিতে, হ্যাঁ, তাহলে শুধু ইন্টিগ্রেশনটা রাখলে 0 টার্মটাই 0 হয়ে যেত, ওয়েট ফ্যাক্টরটা তোমার 0 হয়ে যেত। আমি যেটা বলতে চাইছি, এই যে এই টার্মটাকে আলাদা করে বের না করে নিলে, হ্যাঁ, এই টার্মটা যদি আলাদা করে বের না করে নিতে, শুধু এইটুকু রাখলে তোমার জিরো এনার্জির যে যেটা, সেটা তো ওইটা 0 পড়ে যেত, কারণ এটা 0 হয়ে যেত। সেই জন্য 0 এর টার্মটাকে আলাদা করে নিয়ে বাকিটাকে এইভাবে লিখলাম সেখানে, কারণ 0 এর টার্মটা 0 থেকে লিমিটটা নিলেও 0 এর টার্মটা 0 হচ্ছে, তার মানে অ্যাডিং 0 ইজ নাথিং, রাইট? বুঝতে পারলে? দেন পি বাই কেটি, আর কারোর সমস্যা?
না স্যার, ঠিক আছে।
ওকে, সো
স্যার, স্যার বলছি তাহলে মানে এনার্জি লেভেল গুলো যদি ডিজেনারেট হতো তাহলে তো ওই ওয়েটেজ ফ্যাক্টরটা চেঞ্জ হতো, তাহলে কি এখানে আগে থেকে অ্যাসিউম করা আছে যে ওটা ডিজেনারেট নয়?
হ্যাঁ, মানে আমি যে ওয়েট ফ্যাক্টর নিচ্ছি, ওয়েট ফ্যাক্টরটা প্রত্যেকটা লেভেল, হ্যাঁ, এক একটা এনার্জি লেভেলের জন্য, এক একটা স্টেট লেভেল বলবো না, এক একটা স্টেটের আমি জাস্ট ইউনিট ওয়েট নিচ্ছি, ওয়েট ফ্যাক্টর। আমি এখানে যেটা করেছিলাম, আমি কতগুলো স্টেটকে মানে বাঞ্চিং করেছি, হ্যাঁ, স্টেট বাঞ্চিংটাকে আমি তুলে দিচ্ছি, স্টেট বাঞ্চিংটা তুলে দিয়ে প্রত্যেকটা ইন্ডিভিজুয়াল স্টেটকে আমি দিচ্ছি, হ্যাঁ, প্রত্যেকটা ইন্ডিভিজুয়াল স্টেটকে, এবং ইন্ডিভিজুয়াল স্টেটের, হ্যাঁ, অকুপেশন হচ্ছে, মানে বোসের ক্ষেত্রে ইট ইজ 1, ফার্মির ক্ষেত্রে 1 যদি অকুপেশন 0 আর 1 হয়, আর ক্লাসিক্যালি তো 1 বাই দ্যাট যেরকম ওয়েট ফ্যাক্টর হয়। Okay, so now we have divided by V here. So this is the term, this corresponds to 0 energy, okay, and this is for not 0, okay. Now n by V is like this. Okay. Similarly, we have done the same thing for n by v. For n by v, we have taken, you see, we have taken epsilon equals 0 term outside. What is that? This one. 0 epsilon equals 0 term outside, and then the rest. That is what same thing we have done. And this one is pretty important because this will give you the number of this actually z by 1 minus z. This will give you the number of particles in the 0th energy state, okay, the lowest energy state, and that will correspond to basically if this is a finite number, and this will correspond to the actually condensation. Okay, that will correspond to the condensation. Now this is this intensity is not okay. As we discussed earlier, the distribution curves obeying Bose-Einstein formula statistics merge the classical distribution when this equals to this, the parameter A is irrelevant. And again, we have repeated the same thing that fugacity is less than 1 because mu has to be negative and pretty large. Same logic we have placed again, Z is very less than 1. Therefore, when Z is pretty, so these are the two basic equations, 1 and 2. Okay, so concentrate on this. Okay, these two. Now, when Z is pretty less than 1 corresponds to a situation not far removed from classical limit, the term 1 by V ln 1 minus Z and 1 by V Z by 1 minus Z are negligibly small, right? Certainly, I mean, if we are at the classical limit and Z is pretty small, you see that if Z is pretty small, ln 1 tends to 0, and 1 by V, Z is pretty small, 1 by Z, it is roughly 1, Z is pretty small. It is pretty small. Okay, they will be neglected actually. However, as Z increases and assumes a value close to unity, the term you see Z by 1 minus Z. If Z is approaching 1, then it will be a very small number, and therefore it will be as a whole large number, right? And which can be written as N0 by V. Z by 1 minus Z, that can be written as N0. If you look at the dimension in the equation, you see this is N by V, and it has to be N0 by V0, right? And this is N minus N0 by V, because number of particles is constant, right? So this is N0 by V, N0 being the number of particles in the ground state. Okay. Now can well become significant fraction of the quantity this, because if Z is approaching 1, it can be significant quantity of the fraction Q by N by V. N is the total number of particles. This occupation of a macroscopic fraction of particles into a single state epsilon naught, epsilon equals 0, leads to the famous phenomena of Bose-Einstein condensation. Okay. So probably it is clear that as as it Z tends to 1, then you, at least from these expressions, you have an idea that number of particles in the state with epsilon equals to 0 is going to be large, which is going to be a kind of I mean substantial fraction of the N by V, and that is nothing but the kind of phenomenon of Bose-Einstein condensation. Okay, that leads to the famous phenomenon of Bose-Einstein condensation. Now, N0 by V is, of course, this is the expression. From that, you can write Z in terms of N naught, and therefore you can write V inverse ln 1 minus Z as this. And this is also, this is, of course, negligibly small, you see. If this is like this, and this V inverse, this is of the order of this, and therefore it will be of the order of N inverse ln N. Okay, and therefore This should be negligibly small. And then from the P by KT expression, you can altogether remove the factor that remove the part this you have in the expression number one, that you have this expression, and we have shown in under that situation that this is pretty small, and then you can altogether remove, I mean, you can avoid that. Okay, so you can have this expression, you can just remove that portion, and n minus n0 for this n0 by v is, it could be finite fraction of that. Now let us consider this again, p by kt, substitute x equals to beta epsilon. Again, you have to do some calculations, So, do you mind to do this calculation right now? You consider this, that equation 3 and 4. Equation 3, you can write this way, and you can just change the coordinate, and just can you do these calculations?
Okay, sir.
Correct.
স্যার আপনি কি স্ক্রিনটা অফ করেছেন?
স্ক্রিনটা না তো,
মানে আমারটা তো দেখা যাচ্ছে না, জানি না আমার নেট প্রবলেম তাহলে।
আচ্ছা অন্যটা দেখতে পাচ্ছ?
হ্যাঁ স্যার দেখা যাচ্ছে এখানে।
আমি পাচ্ছি স্যার।
তাহলে আমার সাইটে হয়তো প্রবলেম আছে।
হয়েছে?
করছি স্যার, একটু না।
নোটটা আছে তো তোমাদের কাছে? আমি পাঠিয়েছি না?
না স্যার, তো নেই।
পাঠিয়ে পাঠিয়ে দিচ্ছি। সবটাই পাচ্ছি, অ্যাকচুয়ালি পাচ্ছি থাকলেই হয়ে গেছে। স্ক্রল ডাউন করতে হলে বলবে কোন জায়গাটা। আচ্ছা, একটা জিনিস তোমাদের বলি, এই যে গ্যামা 5/2 এইরকম ভাবে লিখবে, হ্যাঁ আমি অনেক সময় গ্যামার মধ্যে 5/2 লিখে দিয়েছি, হ্যাঁ এই যে তোমরা এইভাবে লিখবে, নোটেশনটা অ্যাকচুয়ালি এই নোটেশনটা এই লাল কালিতে লেখা আছে, উই শুড রাইট।
ওকে স্যার।
ওকে স্যার।
আচ্ছা, কতটা করেছো বলো তো? বলো।
স্যার আপনি কতটা করতে বললেন মানে স্যার যে
আহ, আচ্ছা আচ্ছা, কতটা করেছো বলো, কোন পর্যন্ত? মানে বেসিক্যালি তুমি এইটা ট্রান্সফর্ম করে এইরকম পেয়েছো তো, মানে চেঞ্জিং দ্য ভ্যারিয়েবলস এক্স টু বেটা এপসিলন করে এটা পেয়েছো,
হ্যাঁ
এটা
স্যার
পেয়েছো।
পেয়েছি।
ইন্টিগ্রেশন বাই পার্টস করলে তুমি দুটো টার্ম পাবে, এটা একটা আর এটা একটা। হুম।
হ্যাঁ
এই
স্যার ওটাও
লিমিটটা যদি,
পেয়েছি।
হ্যাঁ এই লিমিটটা বসিয়ে দিলে 0 হয়ে যাবে, ইউ আর লেফট উইথ দিস। নাও দিস ওয়ান, 3/2 I am writing in terms of gamma 5/2, and gamma 5/2 is like this, and therefore I'm just using that formula. Okay. 3/2 is written in terms of gamma 5/2. Okay. And then as it is you have in the integration, then p by kt I am writing 2 pi by h cube, whatever we have actually. We have just done the integration here, and this part is there. So p by kt equals to this part and then this integration. Basically, you can write it in this in terms of this thermal wavelength, and it will be p by kt equals to 1 by lambda cube 1 by gamma of 5/2, and then integration like this. Okay. Then again we are writing the same thing here, p by kt, same thing like this. And now you see, we encounter a function, the integral of the form this. This form is like this, right? N is here, it is 5/2, but it is this for 0 less than z less than, because z has the limit from 0 to 1. Okay. As I said, the chemical potential has the upper bound, that is 0. And therefore z is 1 maximum, and then otherwise it is between 0 and 1. Okay. Now, in the limit, if z tends to 0, now I'm considering this function, which is very similar to this function, except that here n, it is written as n. Okay. Now you see that if your z tends to 0, then if you do this integration, you will find it is it will be a kind of gamma integration. Eventually, it will be z, then this gamma of n, right? Z gamma of n. That, what does it mean? It means that this function is some function of z times gamma of n, right? And that function of n I write as g n z. This is the limiting value. Okay, when z tends to 0, then this comes with this is a constant. This factor will always be there, right? Whether z small or z large, whatever it is. But this function with that function of z, that turns out to be linear, that is z. Okay, but it could be in general when z is not 0, then it is a limiting value, right? And this could be some function of z, and that I name it as small g n z, and therefore your capital G n z should be gamma n times g n z, right? And then g n z I can write it as 1 by gamma n and this, because g n z is this integration. And you see this one and this one. So this part is like small gn, right? Because like this, right? And therefore we can write that small gn as 1 by this in this form, and z inverse. So in what we do in this case, we take this z e to the minus x is a single quantity, z e to the minus x. If it is z inverse, then it will go in the top, it will go as z. So if you write this here, x to the power minus 1, and then you have z inverse means it will go z up. If you take this entire thing in the numerator, it will be z e to the power minus x, and this you have here. Okay, then you see 0 to infinity this, and this one you can sense z is between 0 and 1, it will and it is exponential minus, and it will converge. Assuming that convergence, you can expand it like this, right? And then eventually you will have 1 by gamma like this. This is just series expansion, and you can go over this test and excel, you say xi, and this goes as sum over L equals to 1 to infinity z L by L. Then you see for z pretty less than 1, g and z is of the order of z, right? Now we come back to the situation where P by kt is equals to 1 by lambda q, and this is nothing but g n z, where n is 5 by 2, right? So P by kt is 1 by lambda g 5 by 2 z, and gz for z, small, you can write the expression in this form, okay, as expansion, okay, as long as it is between 0 and 1 or less than 1, then you can have this form, right? So you can write P by kt, then eventually you can write in terms of this function, small g 5 by 2 z. And similarly, if you do the same thing for the other expression, then n minus n0 by phi is 1 by lambda q, g 3 by 2 z. This is number 6. So now we have got this 5 and 6, these two main equations, and then you have to deal with this. Note that again, you see, if you note these two equations, from this, if you eliminate z, then you can get the expression in terms of P, V, N, K, T. Okay, then you can get the equation of state for the ideal Bose gas equation. Okay, using 5 and 6. Okay, so now actually I told that I will not be attending the meeting, but head said that even if late, you come to the meeting once. So maybe I stop here, because in 11:30 I have another class. So please do the calculations up to this by yourself, and in the next class I will try to finish the Bose gas chapter. Okay.
Okay, sir.
Okay.
Okay, sir.